We'll study electromagnetic induction. Electromagnetic induction. See, the question is, we have seen Biot-Savart law. According to that law, if we have a conductor that carries a current, we'll find a magnetic field due to that current carrying conductor. If this is the conductor for this small length dl, you'll find magnetic field, let's say in this direction at this point B, which is given as, you know, this mu 0 by 4 pi, then I dl cross r, if this is r, by r cube. This is Biot-Savart law. That is, what you get is, you get magnetic field due to I, due to a current carrying conductor. This is Biot-Savart law. This we have read. Then we have read IL cross B, the Lorentz force. Lorentz force. What is Lorentz force? It says L cross B. This is, if you place a conductor in a magnetic field, it will experience a force which is equal to this. So we are talking of magnetic field. We are talking of how to get magnetic field due to current. Can magnetic field create current? Just reverse of this. What we have seen up till now, that current can produce magnetic field, and that can and a current carrying conductor can experience force in a magnetic field. This we know. Can magnetic field create current? This is the issue. This is what we are going to study here. Let's say we have a coil. So let this be a coil. This is a wire wound like this. So this is a coil. It is called a coil. The ends are open. Let's say we have this magnetic bar magnet, north south. You know, bar magnets produce magnetic field which is somewhat like this. If you go far away from it, it will be like this. So we have, the direction is this. This is magnetic field. If that, the field lines, if the field lines due to this magnet crosses this coil, that is, it goes through this coil, will there be any effect in this coil? So what we can do, we can put a galvanometer here. We can connect this to a galvanometer. What you will see, if you just place this bar magnet in front of this coil, there will be no movement in this galvanometer. That is, no electromotive force or current is induced in this. Induced, why I am using the term induced? That is induction. Due to this, you won't find any EMF. But if you move this bar magnet towards this side, if you move it, what you will see deflection here. That is, the moment magnetic field, what is this bar magnet doing? This bar magnet is actually changing, producing magnetic field. Now, when you move it, what happens? The magnetic field changes. There is a change in magnetic field with respect to time. So, the moment you move it, you will find some current flowing in this coil. This you can observe in your lab, or even if you have if you can make a coil at your home and you have a bar magnet and you have a galvanometer, you can see this. So this is magnetic field due to this. Second is, if you have a coil, let's say you have another coil and you have connected it to a battery. What happens, you know, once current starts to flow in this loop, in this coil, you have a magnetic field. It may not be like this, it will be like this only. So you will have, if you have some battery connected to a coil, magnetic field will be created. Now if the center of both coils are, you know, kept in front of each other, what will happen? You have a magnetic field, you won't find any deflection. But if you move it towards it or away from it, you'll see deflection. That is what it is doing. A bar magnet was creating magnetic field, it is doing the same thing. So if you move it here or this side or that side, magnetic field will start changing with respect to time, because there will be movement there. So what happens? You will find some electromotive force in this coil. That is because of magnetic field which is changing with time. You have induced current in a coil. Now, what Faraday did, you know the name Faraday? These two observations could be seen anywhere. What he said, he observed and he said that if you don't move this, in place of moving, if you simply put a key here, if you, not a key, a switch here, this is a switch, and you keep on off, doing on off this switch, magnetic field will change. It will be, up, down, up, down, up, down. So magnetic field will start changing. Again, you will find deflection here. That is, Faraday found, and he gave his theory that if the magnetic field inside a coil is changed, an electromotive force will be induced in the coil. Clear up to this? Now, let's understand what is magnetic flux. Before we move forward, what is magnetic flux? Okay, first of all, what is electromagnetic induction? This is induction. Because of magnetism, if you are able to induce current in a coil, or you are able to induce electromotive force, that is called electromagnetic induction. That is I due to B. This is electromagnetic induction. Okay. Now, what is magnetic flux? Let's say this is your magnetic field. This is your magnetic field B, and you have if you have a certain rectangular hole through which this magnetic field is passing. Okay, this magnetic field is passing through this particular area. The area is A, and let's say the normal to the area, this is normal to the area, it makes an angle theta with the magnetic field. Okay, then flux is B dot A, that is, it is BA cos theta. Okay, so what is flux? Flux is magnetic field into area, the normal to the area and the angle between B, that is to be taken into consideration. So this is the meaning of magnetic flux, and it is similar to electric flux that we have already read. So magnetic flux is clear. Now let's see. Okay, so what we have learned up till now, that if there is a time rate of change of magnetic field through a coil, we have a coil and we have a magnetic field that is changing with time. What we observed is that an electromotive force is induced. This we have understood. From here comes Faraday's law of electromagnetic induction. What is it? It says the flux induced in a coil, let it be phi b, denoted by phi b. So if the magnetic field is changing with respect to time, we can show it like this, d phi by dt. Okay, and if this is due to one winding, if there are n number of turns, this will be n d phi by dt. Okay, this is the rate of change of magnetic field proportional to the rate of change of magnetic field. Faraday's law of electromagnetic induction states that this is actually equal to the electromotive force induced in the coil. We are talking of magnitude only. So Faraday's law of electromagnetic induction, it states that the magnitude of the electromotive force in a coil is equal to n number of turns d phi by dt. You can write, generally it is written like this, phi b, that is the flux due to magnetic field, because otherwise we will get confused with flux due to electric field lines. So this is Faraday's law of electromagnetic induction. Here comes Lenz's law. What is Lenz's law? It says that the polarity of the electromotive force is such that the current produced opposes the magnetic field or time rate of magnetic field that produced it. What is the meaning? See, this is the coil, okay, and we have, this is coil, and we have set up changing magnetic field, time rate changing magnetic field, which is n d phi by dt. Okay, this is the changing magnetic field. So if due to this magnetic field there is a current produced like this, which is, let's say, I, then the electromotive force, the direction of the electromotive force is such that it produces a current that opposes it. That is, if the direction is this, you can see this, so the current will be in this direction. So the current induced due to this electromotive force will be in a direction which opposes this. If the magnetic field was this, changing magnetic field was this, the current will be in this direction, so that it opposes this. Clear? So if you now remove the modulus, the magnitude sign, it comes to this. That is, this negative sign is due to Lenz's law, which states that this opposes the field or flux that is producing it. Okay. So this is the expression, combined expression for Faraday's law and Lenz's law. This you should learn by heart. Okay. Okay. Now let's understand the concept of motional electromotive force. This is a very common concept that you should understand. You will find questions also in your exams, because this type of question is, this type of concept is everywhere in the books on physics. That is, let me write it, motional electromotive force. So what is motional electromotive force? Let's understand it. Let's say we have a magnetic field, or to clear things, just let me do cross. Okay, so we have an area which has magnetic field B. Let's say the magnetic field is B, constant magnetic field B. Okay, and let's say we have a loop like this. It is conductor. Okay, these are the open ends of the conductor. Okay, now let's put a rod on this conductor so that this becomes a closed loop, and current will be induced, or electromotive force will be induced only in a coil that is a closed circuit. If this is not there, if this is open circuit, no current will flow. When you close it, current will flow. So let this be PQ. Okay, let this length be L and this length be X. Why I am writing X? Because we will be moving this rod here and there. Let this be rail, and we are moving this here and here. What will happen when we will move this rod from here to here? Our area will change, and because of change of area, flux will change. Clear? So this is X, this is L. What will happen? See, the electromotive force induced in this circuit will be equal to minus d phi by dt. F phi due to B. What is this phi? Phi is B into area, and area is L into X. Okay. Now this is B and L are constants, so we can take them out. What we get is dx by dt. What is dx by dt? Dx by dt is velocity. Dx by dt is velocity of the rod, but it reduces the area. If it is in this direction, dx by dt reduces. So dx by dt is minus v actually. Why? Because as x comes to this side, it will be reducing in nature, the area will be reducing. So dx by dt is minus v. So what we get is BLV. So this is the expression for electromotive force in this type of setup. In questions, you will be given the value of B, L, V or X, whatever, or they can say the area rate of change of area is this. So you will use B and then dA by dt. Whatever it be, the concept is, basic concept is this. Now we have found our electromotive force. Let's say the resistance in this circuit is R. So if we say that the resistance in this closed circuit is R, it would be very difficult to actually calculate out. Why? Because this will be changing, the position will be changing, and then it will be that will affect the resistance also. So let's say this rail part has very insignificant resistance. The only resistance is in this rod. Let that resistance be R, resistance of PQ, and we know electromotive force is this. So current induced will be E by R, and E is BLV. So BLV by R. This is the current in this circuit. Okay. Now when you know what is current, you know force, because there will be a force when you are pushing at this side, there will be a force on this side, or when you are pushing at that side, there will be a current in this side. And what it will be, it is I into length into ILB. This is the force, Lorentz force. So I is BLV by R into LB. So what we get is B square L square V by R. So this is the force experienced by this conductor, and the direction will be opposite to the direction of the velocity. Okay, so now we have found current, we have found force. Next thing is what we want to know, power. So what is the power? Power is, it is force into velocity. This is, F dx by dt. So this is force, and this is V. So what we'll get is B square L square V square by R. This is power. Okay. Now, what is the meaning of this power? Power means if you are moving this rod, you require power. So this value actually gives that power required to move that rod. But where will this power go? While taking it from this side to this side and this side to this side, we require some power, we require some energy. Where will this energy go? This will go as I square R, hit in the this loop, this coil. So I square R will be this P, which is equal to B square L square V square by R. So there are several variables you can, if some of the variables are given and you have to find others, you can find from this equation. So this is motional EMF. I have told you the concept. Try some questions, try some problems on this. You won't feel any difficulty in solving them. This is very easy. Okay.